Hello everyone and welcome to the second topic in the SS2 physics curriculum. Now in this topic what we are looking at is scalar and vector quantities, and we have a number of things that we have to consider in this topic that are very important to every SS2 physics student. Now, to those of you seeing this video for the first time, welcome to our channel. This is Oya Learn, where we discuss different subject areas that help you get better in your academics. Now, do well to please check out our videos and ensure that you are subscribed to the channel. Just click the subscribe button and you can hit the notification bell icon so that you get alerted every time we put out a new content. Trust me, that is one decision you are never going to regret. By clicking that subscribe button, you become a member of our community and you get premium educational content right from this channel, and it is absolutely free. Now, what we are looking at here is scalar and vector quantity. Now, this is something that you are already familiar with. At least you should be able to define what scalar quantities are and what vector quantities are. But we're going deeper than that, because in this topic, we'll look at the meaning of scalar quantities. We'll give you examples of scalar quantities and how you can recognize whether a particular quantity is scalar or not. And then we go to the vectors, which is actually the main part of this topic. We start by understanding the concept of vectors. That is, we define what vectors are. And then we give multiple examples to vector quantities that we have in physics. And then after that, we look at how you represent vector quantities in what we call vector representation. There are quite a number of ways that we can represent a quantity that will let you know that it is a vector quantity. And this happens a lot, especially when you are solving problems in physics. And because the way you would treat a vector quantity is different from how you would treat a scalar quantity. It's important that you know that. So how you then know that in this case you are dealing with a vector quantity and you have to approach it as such is by the way that quantity is represented. So you will learn how to represent vector quantities, and then from there we now go to addition of vectors. We look at different conditions that will warrant different methods for adding two or more vectors together. Now, after that, we then look at how you find the resultant of component vectors in what we call the resolution of component vectors. That is, when you have a particular vector, you can resolve it into its various components. That is, the x component or the y component of that vector. That is, when you resolve it to the horizontal axis or you resolve it to the vertical axis, that is x-axis, y-axis, in each of those cases. Now, after that, we then look at how to find the resultant of more than two vectors. Now, there are cases where an object will be acted upon by more than two vectors. And for you to know the magnitude and direction of the resultant, you must be able to resolve it. So we'll show you how to resolve vectors like this when you have more than two vectors acting on an object. I'll show you the methods by which you can resolve and find the resultant vector, find the magnitude, and also the direction. So trust me, you don't want to miss this. So please get out all your materials as we go through scalar and vector quantities. And please don't forget to like and share the video. It is important to us that we reach many students who need content like this. So please help us to reach them by sharing the video. And if you have any question at all along the process while we are solving questions on this topic or on any of the explanation or even anything at all as touching your academics, we are prepared to answer all of your questions. Please keep them coming. All you have to do is put them in the comment section, and we promise to attend to all of your questions. So thank you very much. Now let's dive into scalar and vector quantity. Let us consider the concept of scalar quantities. We're going to define what a scalar quantity is and describe it so that you fully understand what it is, and then give examples of scalar quantities in physics. Now, when we say a particular quantity is scalar in physics, what it means is that such quantity has only magnitude. Another word for that would be that something that has just size but no direction. There is no direction included when you describe such a quantity. Then that quantity is said to be scalar. So if we're going to define this, we'll say a scalar quantity is a physical quantity that has only magnitude or size but no direction. Let's put that down. A scalar quantity is a physical quantity that has only magnitude. Now we put size in parentheses and no direction. Now, take for example, if a person tells you that they have walked 5 kilometers. Now, in that case, the person has not told you where they started walking from. They did not tell you where they went to. They have not told you the direction in which they have traveled. They have only told you the size of distance that they have covered. In that case, that 5 kilometers there serve as the magnitude of the distance covered by that person. That means distance is a scalar quantity, as it can be understood by just magnitude alone. It does not require direction. The same thing applies to every other quantity that you measure in physics that only requires a magnitude or a number to describe how large or how small the size is. As long as you can understand such quantity by the size of it alone without any direction added to it, then such quantity is said to be a scalar quantity. Now let's mention some examples of scalar quantities. Examples of scalar quantities. Now, like I mentioned, an example would be distance. Okay? Because you can understand this by just magnitude. When I said a person walks 5 kilometers, that's just a number attached to tell you how long of a distance the person has walked. Just magnitude, no direction. Other examples will include temperature. Another one will be mass. Other examples of scalar quantities include what we have as, now when you have something like say energy, time, okay, volume. Now you see all these measurements that I've mentioned, you can understand them by just magnitude. Now in case of distance, you just see the length of path that a person has traveled. You can understand that by just a number, a magnitude. No direction is required to understand that. When we say temperature too, a number can let you know how hot or how cold an object is. For example, if they tell you that a certain volume of water is at 80 degrees Celsius, you have no business drinking from that cup directly like that, because it is very hot and will burn your throat, right? Okay, and if you are told that a particular volume of water is at, say, negative 2 degrees, you know it is very cold, very cold. So all this can help you understand what they describe, the magnitude of it alone. They do not require direction. The same thing with mass. Mass will tell you the quantity of matter that is stuffed into a particular object. That is the amount of stuff in an object. That is the amount of matter in that object. It only describes this by magnitude and no direction. The same thing with energy. Energy can be contained in a body without motion at all. Okay? So it only requires a magnitude. It does not require direction. The same thing with time and the same thing with volume. You see, all these quantities only are described by what? Their magnitude. They are not described by direction. They do not, in fact, require direction for an understanding of them. So any quantity, any physical measurement at all you do in physics, that you can understand them by just a magnitude, or that we say they have only magnitude or size, but no direction, those kind of quantities are what we know as scalar quantities. Now, you can put in the comment section any other scalar quantity that you know. And if you have any question on how you can identify these scalar quantities, or if there's anyone that confuses you a bit as regards identifying scalar quantities, I would love to receive your question. Please put it in the comment section. I will attend to all of your questions. We now know that a scalar quantity has only magnitude and no direction. Now, what is a vector quantity? So let's go through the concept of vectors. Now, when we say a particular physical quantity is a vector in physics, what it means is that such quantity has both magnitude and direction. Now, remember I said that magnitude refers to size. That is, when you quantify how big or how small something is by using a number, then you are referring to the magnitude. But when it is a vector, you don't just use this to describe it. You also have to include the direction. Okay? Vectors involve both what? Magnitude and direction. Now, let's put down a definition for vectors. Okay? So we say vectors are physical quantities which have both magnitude and direction. Now, to further understand this, when we're talking about scalar quantities, I gave an example where I said someone can tell you that they have walked 5 kilometers. Now, in that description there was no direction added to it. We understood that that kind of distance can be measured by just the number attached to it. You can understand that quantity rather by just the magnitude alone. So that makes it a scalar quantity. Now, if someone is telling you, I walked 5 kilometers, they could have gone in any direction at all. So unless that direction is attached to it, you cannot tell you cannot explain it as a vector. Now, to further understand this, take someone who walks on a treadmill during exercise. The person could go the same 5 kilometers on that treadmill and has not left the location where he is. And now compared to another person that has to walk 5 kilometers, say from their house to their school, right? Now, these two people, we see that they both walk 5 kilometers. But the difference is that the other person that was walking on a treadmill does not leave his position. He remains in one point and walks the same 5 kilometers. You don't require direction in that case. But a person who says, I walked 5 kilometers to school, now that person has included a direction. Now you get a full understanding that the person did not just walk 5 kilometers, but he walked in a particular direction. So if you are asked to find such a person, you do not go in the other way. You follow the same path that that person would have gone through. So any calculation you want to do as regards that kind of physical quantity will go in line with the direction in which that person has walked. So you get what I'm saying here now. So in this case, the direction adds more beauty, adds more color to your understanding of what the person has done or the physical quantity being measured. This applies to all vectors. Whenever you are solving vectors in physics, direction helps you understand them better. So it's not just magnitude. That's why we say they have both magnitude and direction. Now, some examples of quantities in physics that are vectors. Examples of vectors. Now, they include displacement. Displacement is a vector quantity. Velocity is a vector quantity. Acceleration is a vector quantity. Force is a vector quantity. Momentum is also a vector quantity amongst many others. Now, when you see displacement, it's referring the distance traveled in a specific direction. That is, it has both magnitude and direction. Velocity is the change in displacement with time. So that is, the person must have moved from one point to another in a particular direction in a specific amount of time. That is how you measure velocity. Okay, you are looking at how fast that object travels in a specific direction. Now, acceleration will be change in velocity with respect to time. And since velocity is a vector quantity, that makes acceleration to a vector quantity. And in the case of force, which is the agent that causes an object to change position, turn, or stop. Now, it acts also on an object in a specific direction because it will make the object to travel in the direction to which the force is applied. So that is, when force is applied, you require the direction in which the force is applied to be able to tell how the object will react to such a force. So you see that it is a vector quantity. And the same thing applies to momentum. So please drop in the comment section other vector quantities that you know, and let's discuss about them. Now let us look at how vectors are represented in physics. Now, vectors can be represented in a large number of ways. We're going to be looking at 3 methods by which you can represent a vector in physics. Now, the first method is the graphical representation. Graphical representation. Now, whenever you are representing a vector graphically, we use straight line with arrow. Okay? So, for example, if you are told that a particular force, which is a vector, is applied at a point, okay, you can represent that force using a vector line. Okay, the same thing applies to velocity, the same thing applies to acceleration and every other vector. You can represent them graphically by using a straight line with a arrowhead. Okay, now what it will look like is something like this. You can then put the arrow like this. If this represents a vector, you see, 2 things you have to note here is that the length of the line, okay, the length of the line represents the magnitude of the vector. Okay, while the arrow shows the direction. Okay, now don't forget that as a vector, it is represented by both magnitude and direction. So when you see in physics that vectors are represented with a diagram that involves straight lines with arrows like this, what you see there is that the length of that line is telling you the magnitude of the vector. Okay, and the arrow is telling you the direction in which the vector is applied. Say, for example, you see an object like this now, and you are told that it moves like so with this arrow here, and then you see something like this, 4 units. Okay, and you are measuring the displacement of this object. If what you are doing here is displacement, it means that what you have here is 4 units of displacement. Now that units could be meters, it could be kilometers, depending on the scale of the graph. Remember that when you scale your graph, you use things like, say, let 1 unit represent 1 meter, or you say let 1 unit represent 1 kilometer. The way you represent your scale will determine how you then transform this unit to the appropriate SI unit for measuring displacement. Now, this same thing could apply to force, could apply to acceleration, and every other vector that you know. So, 2 key things you must note about representing vectors graphically is that the length of the line shows the magnitude of the vector, while the arrow tells you the direction. So now you know that in this case, this object moved from this point to this point, not the other way around. It is in this direction. If to a force too, the force will tell you the direction in which the force is applied, will tell you how the object will react on impact of said force. So don't forget, length of line is what? The magnitude, while the arrow shows what? The direction. Another way by which you can represent vectors in physics is by using mathematical notation or the use of symbols. Now, for this method, there are three ways you can represent a vector. Now, the first way, which let's call that A, would be using bold letters. Now, when you consider some physics prints, you see that there are some letters that are used to denote vectors. They are often written as bold letters. Say, for example, they want to denote velocity with the letter V. They don't just write it the way they write the others. They'll write it as V bold. Now, let me just shade this a bit more so it appears bold to you. This will represent velocity. If it is force, they will then write F like so in bold lettering. Okay? When you see prints like this, where the symbols or the notation for a particular quantity is written in bold, that tells you that such quantity is a vector quantity. Okay? Now, another way you can do this, that is the mathematical notation, is by the use of letters with arrow on top. Letters with arrows on top. Okay? Now, in this method now, you want to denote velocity V. You then see them write something like this, V, and then there's an arrow on the top like this. Or you see F with an arrow on top like this. Or you see P with an arrow on top like this. This is telling you that they are talking about velocity, which is a vector quantity. Force, which is another vector quantity. Momentum, which is also another vector quantity. So when you're reading a physics text and you see them writing or denoting some quantities in this form like this, you know that those quantities are vectors. Now, another notation, mathematical notation, is by using component form. Component form. Now, this one is common, especially in engineering. You see that they represent a particular vector, say V, like this, and they say equals 3I, okay, plus 4J. Okay? Now, what this means is we have two components here, the X component and the Y component. I there represents what? The X component. And then J is your Y component. It's telling you that it has moved a certain distance along the Y component for this, and it has moved 3 units in the X direction for this case. So this is the component form of symbolizing or writing vectors or representing vectors. So it's either you use bold letters like this, or use letters with arrows on top, or you write them in component form with I and J. Now, in cases where you have more than 2 components, another letter can then be introduced. That is I, J, then K as such. So this is how we use mathematical notation to represent vectors. Another way by which we represent vectors in physics is the coordinate or ordered pair method, also known as the analytical method. Now, here you're going to represent a vector by the dimensions, okay? Using coordinates of the dimensions rather. So now, when you have 2 dimensions, we use X and Y coordinates. When it is 3 dimension, we use X, Y, and Z coordinates. So, for example, for the 2 dimension, you could say a particular vector V is 3, 4. Now, what does this mean? It means it is 3 units on X dimension or X direction. Okay? And then 4 units on Y direction. Okay? This tells you the position of such kind of vector by using the coordinates in the X and Y axis. Now, when it has 3 dimensions, a three-dimension vector, say f, a vector, can be represented as 2, minus 1, 5. Okay, what you have here is 2 in x direction, okay, minus 1 in y direction, and then 5 in z direction. So the three dimensions we have here will be x, y, z. So basically, you can say f in the x, y, and z dimension, and this one will be v in the just x and y direction. Okay, so this is 2-dimension and this is 3-dimension way of representing a vector by coordinates or ordered pairs, or what we know as the analytical method. When vectors act on an object, that is more than one vector acting on an object, now the effect on that object follows a path and has a magnitude. Now that effect is what we know as resultant vector. So you may have heard resultant vector before. Now what this means is that a single vector that has the same effect in both magnitude and direction as the original vectors acting on an object. So for example, if you have an object at this point now, and it is acted upon by two vectors, one moving in this direction, another moving in this direction. You see that these vectors take two different paths completely, yet this object is going to move in only one direction. Okay, so the direction it moves and by the magnitude of the vector in that particular direction will give you what we know as the resultant vector. Now, to understand this, let me describe this using the tug of war. Have you ever played the tug of war game before? Now, what happens during tug of war is that you have a particular rope and then you have two teams. Now, these two teams have the goal of dragging a particular point on the rope to their own side of the divide. Now, what they do is they mark that point either using an handkerchief or a colored ribbon. And then the two teams are to hold the rope at their respective position. And then once the whistle is blown, they begin to pull on that rope. Now, what do you see happening in that case? You have a rope like this with a point here. Now, team A, which is at this point, will begin to pull in this direction. Team B, which is at this point, will begin to pull in this direction, right? Now, what happens? Both of them are applying force on the rope, and their force will cancel out at some point when they are the same. But as one force begins to grow more than the other, it will force the rope to move in the direction of the greater force. Hence, what we know as resultant force. So the rope is going to move in the direction not of force A or force B, but in the direction of the resultant force of A and B. So when you have two or more vectors, you need to add those vectors by getting the resultant vector. Okay, so let's define resultant vector. Resultant vector is a single vector which has the same effect in magnitude and direction as the original vectors. So when these two forces begin to pull on the rope, in the end the rope is going to move in one direction, that is the direction of the greater force. Okay, and the magnitude would be in this case the difference of the two forces. But we don't always just resort to doing difference or doing addition. There are factors that determine how you get the resultant of two vectors. Now, the factors that determine that, factors that determine resultant vector. Okay, is 1. Direction of the individual vectors. Okay, when 2 or more vectors are acting on an object, for you to be able to get the resultant, you must consider the direction in which the individual vectors are headed. Okay, that's the first thing you consider. The second thing is the angle between the vectors. Whether the angles is 0, 180 or in between will help you determine the direction of your resultant vector as well. Now we're going to apply this to find the resultant of 2 vectors, and we're going to be using different scenarios. Firstly, we'll look at when the vectors are in the same direction and separated by 0 degrees. And then we look at when the 2 vectors are in opposite direction and separated by 180 degrees. Now you see these 2 cases are often called tail to tail or tail to head. Okay, now when they are in the same direction, we call that tail to head, or head to tail rather. And then when they are in opposite direction, we say tail to tail. Now there's other cases where they are separated by a given angle theta, which we'll also consider, which may lead to what we know as the parallelogram law of vectors or the triangular laws of vectors. So we get to solve vectors using these different scenarios, starting first with the case when the 2 vectors are in the same direction separated by 0 degrees. Let us look at how you will find the resultant of 2 vectors when the 2 vectors are in similar direction separated by 0 degrees. Now to explain this concept, let's consider, for example, we have an object. Now if you recall what we did when we were talking about friction during our SS1 topics, we talked about the fact that before an object will begin to move, you must overcome frictional force, right? So let's assume that this is an object A, okay, which requires a minimum force of 10 newtons before it can begin to move. Now if a person comes and applies in this direction now 8 newtons, because this is not enough to overcome the frictional force, the object will not move. Now for it to move, you must add more force to it. Now you don't just go about and apply the force at any point on this object. Because you want it to move, you have to apply the force in the same direction as this one, because you want to add them up. It's just kind of like what happens when you're trying to push a car. When you're trying to push a car, you don't have some people stay at the front and push while another person stay at the back and start pushing. They would cancel each other out. So the force has to be applied in the same direction. Now we are using this because that's what we are considering here. The vectors are in similar direction separated by 0 degrees. So now let's assume another person then comes in and applies, say, 6 newton of force. How you get your resultant force is that the resultant force will be in this direction. Okay, now what does this state? It says when you have 2 forces, when 2 forces, 2 vectors, P and Q, are in the same direction, separated by 0 degrees. Now another way they could say this is that they are parallel vectors. Okay, vectors that are parallel are in the same direction and have 0 degrees separating them. Okay, now your resultant vector, the resultant vector is given by R, which means resultant vector, equals vector P plus vector Q. So that is, in this case, the resultant vector R here would then be 8 newtons plus 6 newtons. And this would give us 14 newtons. And we know that the direction is in this direction of R. So the two forces here add up to give you R, which is acting in the same direction as the individual force. That is, if you don't want to use these two people which are applying 8 newtons and 6 newtons, but you want the same effect that these two forces is going to give object A, all you need is just get one person that can apply 14 newtons of force in the same direction, and it will have the same effect as these two people, which is actually the definition of resultant vector. Remember, it says a singular vector that has the same effect in magnitude and direction as the original vectors. Now, key thing you should never forget in this case is that when two vectors are in same direction and are parallel to each other, that is at 0 degrees, the resultant R is given as the sum of the individual vectors. Let's solve some questions on this to further understand it better. Looking at this question, it says a man walks 4 kilometers east, then continues walking 6 kilometers east. What is his total displacement from the starting point? Now, let's solve this problem. Now, one thing I tell students is that sometimes there are some information that may not be as clear as what you see here. But one thing that can always help you solve a vector problem without error is to first represent what you see in the question by using your graphical representation. Remember when we talked about representation of vectors and we say you can represent it using a straight line with arrow, right? Good. Now let's consider this as the starting point A of the man. At point A, he moves 4 kilometers east. Now, your cardinal points, when you draw them, they look like this, right? Where this represents north, this is east, this is south, and this is west. I hope you remember this. So if we are going east, it means we are going towards the right. So we go like this to the right, in this direction. And what is the magnitude? We've seen direction already. The magnitude is what? 4 kilometers. This means 4 kilometers east. It gets to a point, let's call this point B. And then continues walking 6 kilometers east. That is, from this point, he then continues to the east also, which is right direction. We continue again, and we make this slightly longer than the first one. Don't forget to put the arrow. And then it gets to the stop point, which we are going to call C. And this is what? 6 kilometers. Okay? Now we are asked to find the total displacement from the start point. Now remember how we talked about solving for vectors in the same direction separated by 0 degrees. You see that the first displacement is in this direction. The second one is also in that same direction. And there's no angle separating them. That is, they are parallel. They are in the same direction. So what do we do here? Remember, resultant R equals P plus Q, right? So that means its total displacement would be 4 kilometers plus 6 kilometers to give you 10 kilometers. And since they are still in the same direction, we'll indicate that to the east, 10 kilometers east. And truly, displacement is supposed to be the total length of space represented by the shortest possible straight line. Okay? So if this is point A and this is point C where it ends, and we join it with just one straight line, it is actually the addition of these two, as you can see as well. So the answer remains 10 kilometers east. This is a slightly more technical question as regards finding the resultant of two vectors. Now this says that two forces, F1, 12 newtons, and F2, 7 newtons, act in the same direction on an object of mass 3 kilograms. Now, if these forces are applied simultaneously, what is the acceleration of the object? Now, some students may think, okay, let's find the acceleration when you apply force F1, 12 newtons, and then when you apply force F2, which is 7 newtons, and then add their acceleration together since they are in the same direction. Now, you will get the same answer, right? But it defeats the objective of this question, because the question tells us that the forces are applied simultaneously. Now, this is why oftentimes you could solve a problem in physics, get the answer exactly the same as what the teacher says the answer is, but still get the question wrong. You have to go through the entire thing that the question says. In this question, we see that the two forces are applied simultaneously. What this means is that those two forces are going to give us a resultant force that will give us the same effect in magnitude and direction as the individual forces being applied. So the first thing you want to do is to find the resultant force. After that, you can then find the acceleration of the object. So here's the solution. Now, we say let the resultant force be F. And F is going to be F1 plus F2, which means we have 12 newtons plus 7 newtons, which would give us 19 newtons. So the resultant force is 19 newtons in the same direction as the individual forces F1 and F2. Okay? Now, to find acceleration, we're going to apply the equation F equals ma. Now, this is gotten from the second Newtonian law of motion. Now, you are already familiar with this equation, but we are still going to do a little more about it when we start looking at the laws of motion. Okay, but don't forget F equals ma. So what this implies is that the acceleration A would then be force divided by mass. Now, the resultant force F is 19 newtons divided by the mass. The mass is given in the question as 3 kilograms. Now let's divide. 3 is going to go in 19 how many times? That's 6 times with a remainder of 1. So 6 whole number 1 over 3. And the unit here would give you meter per second squared. Now you can write this in decimal by saying 6.33. You see it is 3 recurring. So I'm going to just do it in 2 decimal places. So 6.33 meter per second squared. So either of these two is correct, but I prefer that you leave it in decimal form like this. So once again, don't forget, you always have to find the resultant in this case since they apply simultaneously. Then from there you can then apply other equations to find what the question itself is asking that you find. I hope you understand what we mean. If you have any other question on this, please ensure you put it in the comment section and we'll definitely attend to all your questions. Now, what happens when you have two vectors acting on the same object but in opposite direction? Now, we often say this is to find the resultant vector of two vectors in opposite directions separated by 180 degrees. Or as some will have it, they will say tail to tail, opposite direction. So to understand this, take for example an object A being acted upon by two forces. One in this direction, the other in the opposite direction. Now, you know that this object is only going to move in one direction in the end. And that direction will be the same as the resultant of the vectors. Now, how would you get this? Both of them act in opposite direction and have their individual magnitude. Okay, the one with the greater will cause more effect on its side, which will then make this object to move in the direction of the greater one. But the effect it will have on it will not be the same as if it were just this particular vector that was acting on it. Let's understand this. Let's assume now for a moment that there isn't this particular vector acting at this point. This vector is not there. When this vector is non-existent, this object will move in this direction with the effect that the magnitude of this vector applies on it. The moment you apply another vector now in the opposite direction, it will diminish the effect of this vector. Now, because this vector is still more than this, it will still continue in this direction, but at a slower rate. That is, the effect has been reduced. It's just like this. If this were 10 newtons, for example, and this were 6 newtons, it will move in the direction of the 10 newtons. But the effect will not be the same as if it were just 10 newtons that was pulling it in this particular direction. It will give you a smaller effect. So which is why when you are solving vectors like this, so when you have when two vectors P and Q act on an object in opposite direction, the resultant R is given by R equals P minus Q. So in this case, resultant R will be 10 newtons minus 6 newtons, which will give you 4 newtons in direction of 10 newtons. It will go in direction of the 10 newton force, but with an effect of just 4 newtons. Let me test you further. Imagine now you have another object B, and it is acted upon by a force in this direction, which is, let's call this 6 newtons, and then this one, let's call this 7 newtons, and then another force in this direction, which we're going to call 20 newtons. What do you think will be the resultant in this case? Now you see here that we have combined these ones that are in the same direction, two vectors in the same direction, with another one that is in the opposite direction, right? So you see that your P is 20 newtons here, and your Q is actually the resultant of these two. And what will be the resultant here? 6 newtons plus 7 newtons, which would give you what? 13 newtons. So your effective resultant vector here will now be what? 20 newtons minus 13 newtons, which would give you what? 7 newtons in direction of the 20 newtons. I hope you understand this now. Let's apply it now to other questions and then see how you solve resultant of vectors in opposite direction. This question says, find the net displacement of a boy who walked 9 meters east and 5 meters west. Now, if you're yet to be subscribed to the channel, I'll encourage you to please do so. It's only going to take a moment of your time. Just click the subscribe button, and you can also click the notification bell icon so that you always get alerted every time we put out a new content. Now, to solve the resultant displacement or the net displacement of this boy, what do? We apply this rule that resultant is P minus Q. Now, the resultant in this case is the net displacement. And the initial displacement, now, the reason why we know that it's in opposite direction is simple. When you have your different cardinal points, like in this case, we have north here, right? We have south, this is east, and this is west. So you see that east is in this direction, west is in the opposite direction, just as north and south are in opposite direction of each other on the cardinal points. Good. So, and since it moves east, then west, we know that it's going the reverse direction by the time it goes 5 meters west. So that's why we are applying the P minus Q to get our resultant, because they are in opposite direction. So the first displacement we have is 9 meters minus the other displacement, which is 5 meters. And this would give us in total 4 meters. And the direction will be in the direction of the greater one. So the greater one is 9 meters, so it's east, so it is 4 meters east. Now let's look at it this way. Starting at this point here now, someone goes like this, 9 meters. Okay? And then returns back like this, 5 meters. Okay? You see that this is where he ends up. And if this is his start, he has only moved in this direction, which is still to the east. So you see why the answer carries east now. So either way, whether I use the diagram to solve it or you use this analytical method to solve it, you will end up with the same answer, which is 4 meters east. Now in this question here, we see this diagram where we have an object A, which is 7 kilograms. That should be the mass, and it is acted on by 3 forces, F1, F2 and F3, and their magnitude is shown. This is 9 newtons, 9 newtons, 25 newtons. Likewise, their direction as indicated by these arrows here. Okay, and the question says we should find the acceleration of object A acted upon by F1, F2 and F3 as shown in the diagram. So what you need to do in this case is, now since these forces are acting simultaneously, you need to find the resultant force, and then from there you find the acceleration. So here's the solution. Now the first thing we want to do is to find the resultant R1 of F1 and F2, and that is F1 plus F2, which will give you 9 newtons plus 9 newtons to give us 18 newtons. And the direction is the same as F1 and F2. And then the overall resultant would then be F3 minus R1. Now, you could have solved this straight up by just saying F3 minus, then you open parentheses, F1 plus F2. Okay? It will still get you to the same place. But I'm just solving it in steps so that you understand the process. Now, in this case, what we have is F3, which is 25 newtons, minus R1, which is 18 newtons. And this would give us 7 newtons. And you know that it's in direction of F3. Okay, since it's the larger one there. Now, to find the acceleration, recall that F equals ma, which implies the acceleration A is F over m. Okay, where F here is the resultant. F is our resultant R. So acceleration of the object would then be given as the resultant force acting on the object, which is 7 newtons, divided by the mass, which is 7 kilograms. And this is going to give us 1.0 meter per second squared. Now, this is how you solve resultant vectors for two vectors in opposite direction. If you have any question on this, please put it in the comment section, and please help us to share the video so that many more can learn this process. Another way by which you would have to find resultant vector is in the case when you have two vectors that are inclined to each other. Now, you recall that we have looked at when two vectors are in the same direction. We have also seen when they are in opposite direction, and the angles there is 0 degrees and 180 degrees respectively. But in this case now, when you have two vectors inclined at an angle theta, how would you find the resultant? Now, there's this rule in physics that is applied whenever you have two vectors inclined at an angle theta, and that rule states that when you have those two vectors such that they are inclined at angle theta, they could represent the adjacent side of a parallelogram, which is why that rule is known as the parallelogram law of vectors. So let's note that the parallelogram law of vectors. Now, what this rule states is that if two vectors are represented both in magnitude and direction by the adjacent sides of a parallelogram, then the diagonal drawn from the point of intersection of these two vectors represent the resultant both in magnitude and direction. Now, what does this mean? Let's take, for example, we have vector 1, V1, and vector 2, V2, inclined at an angle theta, like this. Now, what the rule is saying that we can complete this to make it a parallelogram, such that we mirror vector 2 up like this, and vector 1 like this. Okay? Now, it has complete a parallelogram. And you know what? Something about parallelogram. This angle and this angle are the same, just as the angle here and the angle here would be the same, right? So, but what they're not saying now is that if you split this in two, that is, you draw a diagonal like this, such that what you have here is equal to each other, right? Then this here would be your resultant of V1 and V2. That's basically what the law states. But let's write the law down so that we remember. This states that if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram. Okay? The diagonal drawn from the point of intersection of the vectors represents the resultant both in magnitude and direction. Now, what this means is just what you can see in this diagram, where you have vector 1 and vector 2 like this being the adjacent side of this parallelogram. Then the diagonal drawn from the point of intersection like this is a diagonal, would then be the resultant vector representing it both in magnitude and direction. The direction being like this, since V1 goes this way and V2 goes like this. So if you apply a vector in this direction and another in this direction, the effect of these two vectors on the object at this point would be represented in magnitude and direction by this line R. Now, let me show you the mathematical representation of this from the diagram, and then we apply that to solve a few questions on the resultant of vectors inclined to each other. So let's apply the rule using this diagram now. So you see here we have two vectors P and Q here, which are the adjacent sides of this parallelogram. Now recall that the resultant is the line drawn like this from the point of intersection going in this direction. This would be R. Now, there are two ways you can solve a case like this to find the value of this resultant. You can either work with what you have here, okay? You can work with what you have here, or you apply the other rule, which I will then show you in just about a little bit. Let's look at what we have here. Now, if you're going to use this here to solve, you know that what you have here also represents P, right? Now, this will look like a scaling triangle, which you can solve using the cosine rule. And if you are solving using the cosine rule, you know that R squared would then be the square of each of these, that is P squared plus Q squared. Then you say minus 2PQ cos alpha. Okay? Now, what is the relationship between this alpha and this theta, especially when it comes to cosine? When you are finding the cosine of these angles, the relationship is that, you see, cos theta is actually negative cos alpha. Okay? That's how they are related to each other. So if you're going to apply it there and put in cos theta to this case, you would then say R squared equals P squared plus Q squared minus 2PQ minus cos theta. Now, look at this. negative sign, they multiply out. So you then have r squared, which is the square of the resultant, equals p squared plus q squared. Minus times minus will give you plus, and then 2pq cos theta. So when you have two vectors that can be represented both in magnitude and direction by the adjacent side of a parallelogram, such that the angle of inclination is what you have here, which is theta, you can find the resultant by applying this equation. This equation is what we know as the parallelogram law of vectors. Now, here's something that examiners often do. Sometimes they would ask you to find either the resultant or any of the vectors, and then instead of giving you the angle of inclination that we have here, they would rather give you this part. So you can just go ahead and just use this cosine rule direct, and then you will solve it without a problem. Okay? But if you are given this angle here, the angle between the two vectors, then the sign changes to plus here. But if what you are given is this other one, the sign changes to negative. Okay? And then you can then solve. Now, please take note, there are some angles you need to know the sine of, the cosine of as you work with. So in this case, we use cosine a lot. So you would have to know the cosine of some special angles like 0, like 30, 45, 60, and 90. When you know this, it helps you to be able to solve problems like this without having to use calculator too often. Okay? So please, if you don't know that yet, learn it and try to memorize angles like 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. It will help you solve questions like this without problem. So now that we can represent the parallelogram law of vector in simple equation like this, let us apply it to solve some questions. This question from the UTME 2008 says that the resultant of two forces, 12 newtons and 5 newtons, is 13 newtons. Now, what is the angle between the two forces? Now, you see in this question that we are not given the angle of inclination, but this follows the condition when two vectors are inclined to each other, because you are asked to find the angle of inclination, right? So we can apply the parallelogram law of vectors to solve this question. So here's the solution. Now, when you see questions like this, just try to remember the equation itself, which says that the square of the resultant equals square of the first one of the vectors plus square of the other, then plus twice the product of the two vectors cos the angle of inclination between them. Now, you can first try by making theta the subject of the equation here, or you just impute the values you have from the question and then solve till you get the value of theta. So let's do that. We already have the resultant. The resultant is 13 newtons. So we go on and say 13 squared equals, now one of the forces is 12, so 12 squared plus 5 squared plus 2 multiplied by 12 multiplied by 5. All of this multiplied by cosine theta. Now, we do not know what the value of theta is, so we leave it like this. Now, let's resolve what we have here. Now, what is 13 squared? 13 squared will give you 169. Equals, now what do we have here? This is 144 plus, this is 25 plus, now what we have here is 2 times 12, then times 5. We can just go easy and say 2 times 5 first, that gives you 10. And 10 times 12 will give you 120. 120 cos theta. Now, all we need to do is try to make cos theta the subject. So let's tidy up. Here now we have 169 equals 144 plus 25 would give you 169 as well. 169 plus 120 cos theta. Now, from here, when we make 120 cos theta the subject, what you have is 169, then this crosses over and becomes minus 169. That is 120 cos theta is therefore 0. So from here we can then say cos 0 equals 0 divided by 120. So that means cos theta is still 0. Now, how do we find theta? We find the inverse cosine of 0. So theta itself becomes cos inverse of 0. Now, what this means is that cosine of what angle will give you 0? And cosine of 90 is what will give you 0. That means the angle of inclination is 90 degrees. Now you see how you can apply the parallelogram law of vectors to solve questions when vectors are inclined at a certain angle. Let's solve more questions on this. This is another 2008 UTME question. Let's look at what the question says. A body of mass 4 kilograms resting on a smooth horizontal plane is simultaneously acted upon by two perpendicular forces, 6 Newton and 8 Newtons. Calculate the acceleration of the body. Now, I'll help you to some extent here. Now, look at this. Let me point out a few things for you though. Here you have the mass. You are asked to find the acceleration, but the object is acted upon by two perpendicular forces. Now, what do we get from there? First thing is that those two forces will have one effect, and that effect is known as the resultant force. So you have to find resultant force, and you can apply the parallelogram law of vectors. Yes. Now, after you find that, you also know that acceleration can be gotten from using the equation F equals ma, where F is force, mass is given here, and a being the acceleration, which is what this question asks you to find. And the force there is the resultant force on this object. So what you need to do is first find the resultant force F, and then find the acceleration of the object. Now at this point, you can now pause the video and try it out yourself, following those steps I just laid out for you. Now, I would like to know if the answer that you got is the same as what is gotten at the end of this video. So please ensure that you put your response, your answer, lock it in the comment section before you hit play again. Alright? So let's see how you did. Now, the first thing we want to do is to find the resultant force. Now, the resultant force, so solution. The resultant force R squared would be the square of the individual forces. So we have 6 squared plus 8 squared plus, okay? And then we're going to have 2 multiplied by 6 multiplied by 8 multiplied by cosine of, now remember it's perpendicular, so that means it is 90 degrees. Good. Now let's go on. R squared therefore becomes 6 squared will give you 36 plus 8 squared will give you 64 plus, now what do we have here? 2 times 6 times 8. Now that will give us, now 2 times 6 is 12. 12 times 8 should give us, now see that, 96. So we have 96 multiplied by cos 90. Cos 90 is going to give us 0. So all of these end up being 0. So our resultant force is therefore 36 plus 64, which is 100. Now remember this carries squared. So to find the resultant itself, you have to find the square root of 100. And that will give you 10 newtons. Now we have our resultant force. So resultant F equals R, which is 10 newtons. Now when you apply F equals ma, what does that mean? We can then find our acceleration by saying F divided by mass, force divided by mass, where force is the resultant. So we have 10 divided by the mass of the object itself is 4. Okay? Now what does this give us? What we are going to be having here is 2.5. And the unit of acceleration is meter per second squared. So you see, all you need to do is first find the resultant, then apply it to F equals ma to find your acceleration. Don't forget to put your comment of the answer Drop the comment of your answer in the comment section and then we'll pick it from there. Let us look at this SSE question that reads, two forces whose resultant is 100 Newton are perpendicular to each other. Now, if one of them makes an angle of 60 degrees with the resultant, calculate the magnitude. Okay, now when you have questions like this, you see that we have the resultant, we have the angle that they make with each other, but we have two unknown here. We don't know any of the two forces. So applying the parallelogram law of vector will not work because there we have two unknown. Okay, so if we want to solve one of them, one very good way to apply, one method to apply that will help you solve it without error is to first draw your vector diagram, right? And then that will lead you to see which method will solve the problem better. Okay, so let's try to represent this question with a vector diagram. So here's the solution. Okay, we have two forces according to the question that are perpendicular to each other. So let's draw that. Two perpendicular forces. You can then name them F1 and F2. They are perpendicular. Now, how would you get the resultant of these forces? Now, the resultant goes from the point of intersection like this way. Okay, now we can make this into a triangle either by doing like this or like this. Okay, applying the parallelogram law. Okay, so once you do this, this is what you're going to have. Okay, now what you have here represents F1 as well, so F1 prime, while this remains F2. Now the question goes on to tell us that the one we want to solve for makes 60 degrees with the resultant. So if I want to solve it for F1, I will make this angle 60 degrees. If I want to solve it for F2, I will make this angle 60 degrees. But note that both of them cannot be 60 because this is already a 90 degree. So anyone you pick will affect the other one. So you can decide to solve for F1 or F2. So let's solve for F1. If I'm going to solve for F1, I will make the angle like this. F1 makes 60 degrees with the resultant R, which is 100 newtons. So now you see that what we have is a right angle triangle that looks like this. 60 degrees, 100 newtons, and F1 like this. Now, when you have cases like this and that you have to solve, you see that we have an angle, we have the hypotenuse side, and one of the sides. This makes the adjacent of this right angle triangle. So we're going to apply the trigonometric ratio, often known as the Scalar. Okay, so we are trying to find F1, which is the adjacent side, and we have the hypotenuse. So that means the cosine would be the one that will work, the cosine ratio. So cosine ratio says that the cosine of the angle, which is in this case is 60 degrees, will be the ratio of the adjacent side, F1, to the hypotenuse, which is 100 newtons. Now, the cosine of 60 degrees will give you 1 over 2. And 1 over 2 therefore equals F1 over 100 newtons. Now, what this means is that F1 therefore becomes 100 newtons divided by 2, which would give you 50 newtons. Now, take note. If I have chosen to solve for F2 instead and say let F2 be the force that makes 60 degrees with the resultant, I would have still gotten 50 newtons. What matters here is that they said that the force we are trying to solve makes 60 degrees with the resultant. So whichever one you pick is what you are going to solve for. Now you can then go on to solve the other one if you like. Now that we have the adjacent side and we have the hypotenuse, we can then apply Pythagoras theorem to solve for the other one. You can do that and then drop the answer in the comment section. Thank you. Another aspect of vectors that you need to understand is resolution of component vectors. Now, first, let's start by understanding what component vector means. Okay? When you have a given vector, the component of that vector in a given direction signifies the effective value in that direction. Now, let's put that down. The component of a vector in a given direction is its effective value in that direction. Now, as far as this goes, at this level in physics, the components of vectors that we often solve for is the horizontal component and the vertical component. So when we say the horizontal component of a vector, you are looking at the effective value of that vector along the horizontal axis, or otherwise known as the x-axis, while the vertical component will be the effective value of that same vector along the vertical axis, or what we know as the y-axis. So if you have something like this now, where this is the y-axis and this is the x-axis, okay, and then we have a vector in this direction here, okay, which has an angle theta with the horizontal. Now, oftentimes when you are solving for resolution of vectors like this, we oftentimes take our angle to the horizontal. It makes it easy to develop an equation for this. We don't have to always have to solve and apply methods or derive answers. We rather prefer to use equations to get to where we are going. It's easier that way. So we just take the angles to the horizontal and then we have a workable equation for whether you are doing horizontal component or vertical component. So you can put that at the back of your mind so that anytime you are solving for components of a vector and you are given the angles to a certain side, whether to the vertical, you can always find the same angle now to the horizontal instead. That way you can then apply the equations that we're going to derive in this video. Now, this would be our vector v. Okay, so if you trace this down like this, you will get the effective value along the x-axis, which would be the component, the horizontal component. So we call that v of x. And then when you trace it to the vertical axis like this, you will get the vertical component of the same vector v, which we will now call v of y. Okay, so now let's note that here. V of x is horizontal component of vector v, and then v of y will signify the vertical component of vector v. Now, when you apply your trigonometric ratios, you can get the value of v of y and v of x. There's a simple equation that makes all of this way easier. You see, v of x can be gotten by saying v multiplied by cosine of theta. As long as this angle is to the horizontal, it will be cos theta. Let me explain this. Look at this now. We want to find v of x. You have something like this, right angle triangle, and you have theta here. Remember, this will now be what? Adjacent. While this is what? Hypotenuse. Okay? Remember that so, ka, toi. Okay? For the adjacent side, you need what? Cosine ratio, so that you can get adjacent over hypotenuse. So cos theta ought to be the adjacent. See it? Cos theta is supposed to be adjacent over hypotenuse. Now what this implies, since it's the adjacent side we need, we now say adjacent equals hypotenuse cos theta. That's just what happened here. Hypotenuse is v, cos theta. Very simple now, right? So this is the horizontal component of vector v. Now to get the vertical component v of y, all you need apply is v sine theta. Because now what you are looking for is this other side, okay, which is the opposite. Okay, so opposite over hypotenuse. The same method, and you will see that the vertical component will then be what you have here, which is what? The hypotenuse multiplied by the sine of the angle to the horizontal. Now, once again, I'm stressing this so that it sticks. The angle you have to apply when solving for components of a vector like this has to be taken to the horizontal if you want to apply these formulas. Okay? However, if you want to go by the normal analytical method of solving it, you want to go through this route, you can choose whether it's to the vertical or to the horizontal. You can still solve it. You will still get the same answer, no doubt. Okay? But to save you the stress is why we apply this method. So for example now, if I give you a case like this, let's just look at something like this now. And then I have my vector like this. And then instead I give you this angle here. Okay? And then I call this alpha. Remember that what you want to apply is theta. So what do? You find this part, theta, which is actually 90 minus alpha. Okay? So in this case now, you just say v of x equals v cos. Okay? And what is the value of theta? 90 minus alpha. And then v of y will be v sine 90 minus alpha. So it always works as long as you remember to always take your angle to the horizontal. Let us now apply this to solve a few questions on resolution of component vectors. In this question, we are asked to resolve a force of 100 newtons inclined at 60 degrees to the horizontal into its horizontal and vertical components. Okay, so to solve this, we can easily apply the equation because we are given the angle to the horizontal. So we say in our solution, our horizontal component, since it is force, let's just call that f of x instead, rather than using vector. So f of x will now be f cos theta. Now what that means is that the horizontal component will be the force itself, which is 100 newtons, multiplied by cosine of 60 degrees. Now this will give you 100 newton multiplied by cos 60 is 1/2. And this would give you 50 newtons. Okay? Now, for the vertical component, f of y, that will be f sine theta, which means we have 100 newtons multiplied by sine 60 degrees. Now, what does this mean? We will have 100 newtons multiplied by, now I'll put this in decimal, sine 60 is 0.866. And when you multiply it by 100, that will give you 86.6 newton as the vertical component of the force F. I hope you understand this. Horizontal component f of x is f cos theta. Vertical component f of y is f sin theta, which gives us 50 newtons and 86.6 newtons respectively. In this question, we are told that a nail on a vertical wall is pulled by means of a cord attached to its head. Now, if the cord makes 60 degrees with the horizontal axis and exerts a force of 100 newton on the nail, we are to find first the effective force which tends to pull the nail out of the wall, and then finally the force which tends to bend the nail. Now, to make you understand this question, I'm going to start with a vector diagram. Let's say this is the wall itself, okay? And then we have the nail, like so, and then a cord is attached to it that pulls in this point, where we have the tension T equals 100 newtons. Okay? You see that it makes 60 degrees with the horizontal here, which means we have a vertical here. Now, this would be T of x, while this would be T of y. Okay? So, the one that tends to pull the nail out is T of x, while the one that tends to bend it would be our T of y here. This T of x pulling it out, T of y is what is bending it. So, to solve the first part, the one that is pulling it out would be the horizontal component of T. So, T of x would then be T cos theta. So, what we have there is T itself is 100 newtons multiplied by cos 60 degrees. So, what we have here implies that T of x, that is the force that pulls the nail out of the wall is 100 newtons multiplied by half, which would give you 50 newtons. Okay? And then for the B part, T of Y, that which tends to bend the nail, would be the force itself, which is the tension in the cord, multiplied by the sine of the angle. So what we have here is 100 newtons multiplied by sine 60 degrees. Now this would give you 86.6 Newton. So the force tending to bend the nail is 86.6 Newton, and the force tending to pull it out of the wall is 50 newtons, which give you a resultant force of 100 newtons. This question says, a boy is pulling a load of 150 newtons with a string inclined at an angle of 30 degrees to the horizontal. Now, if the tension in the string itself is 105 newtons, the force tending to lift the load off the ground is, now in this case, we see that the force that has to lift it from the ground is the vertical force. So we are looking for the vertical component of the force. So, and since the tension is already given as 105, so T of Y is what we are asked to find. And that will give us T sine theta. So T of Y is therefore 105 newtons sine 30 degrees. And this would give us 105 newtons times 0.5, which would give us 52.5 Newton. Now, there's something to note from this question. The load itself is 150 newtons. So to lift it, you have to apply more force than this. That's even assuming that friction is minimal. So in this case there, you can then say that this force is not sufficient to lift the load. The reason why we can solve this without any problem is because the question itself says the force tending to lift. It does not say the force that lifts the load. If the question has said find the force that lifts the load, it is not going to be 52.5 Newton. We have to find the force that is enough to overcome that load given the friction at that particular point. So one thing to note is that in this question, what we have solved here is the force that is applied along the vertical axis if the rope were to be applied on the vertical axis there. Okay, it is not sufficient to pull the load, but what we have there is 52.5 newtons. There are some cases where a particular object will be impacted by more than two vectors. So let us learn how to resolve these kind of cases. Okay, so when you look at the diagram that we have here, we have an object here that is impacted by four forces: F1, F2, F3, and F4. Now, remember that when we're talking about component vectors, I said one easy way to solve them is to take your angles to the horizontal. So you see that the angles we have taken here are to the horizontal. All these angles here are to the horizontal. We have theta 1, theta 2, theta 3, and theta 4. Now, how do you resolve cases like this? Now, step 1 involves you finding all the x components. Okay? And then step 2 will involve you finding all the y components of the vectors. And then you then go on to find the resultant. Okay? Now, step 1. Find the horizontal component. X. Now, how do you find the horizontal component? Now, I'm going to quickly refresh your mind on something you should know from mathematics. Now, we have something like this, the quadrants, okay? Now, we often use things like this, C-A-S-T, some say A-C-T-S, depending on how you like to remember it. Where here, we have sine, cosine, and tan, all positive. Here, only sine is positive. Here, only tan is positive. And here, only cosine is positive. I hope you remember something like this, where this is your first quadrant, which is 0 to 90. This is your second quadrant. This is the third quadrant, and this is the fourth quadrant. So it applies in this case too. So when you want to solve this, remember that your x is remember, vector of x is vector cos theta, right? So we are applying cosine. So let's start with this. You see that F1 here is in the first quadrant. So x, to find the value of x, you do this. You have to be very careful with the angles you are working with. The angle here is in the first quadrant and all is positive here. So it will then be F1 cos theta plus, now F2 is in the second quadrant, and in the second quadrant only sign is positive, which means cosine will take negative. So you come like this and say minus first, then F2 cos, remember this is theta 1, so this will be cos theta 2. Is that clear now? Okay, now you then continue and say plus. Now what we have here is in the third quadrant, only tangent should be positive here, so we are working with cosine, this will also be negative. So minus F3 cos theta 3, and then finally plus the fourth quadrant where cosine is positive, so that will be F4 cos theta 4. This is how you get your x component. You can write this down so you do not forget. Now let's look at the y component. For your y component, you follow the same process, except that you have to be careful here because first and second quadrants are positive for sine. So that will mean we have F1 sine theta 1 plus F2 sine theta 2, because at these two stages sine is positive. But here sine becomes negative. It now becomes plus negative F3 sine theta 3, then plus negative F4 sine theta 4. Now when you apply this, you can then get your x component and your y component. Then to finish it up, which is the resultant vector r, will then be given as the square root of x squared plus y squared. Now note, the answer you get for x here can be positive or negative, showing the direction, because it could be going in the positive x direction or the negative x direction. And the same thing applies to y. It can be positive or negative. It can even be zero, showing that there is no effective vector in the x direction or in the y direction when you get zero. Okay, so it can be positive, negative, or zero. And you still have to apply it in this equation to get your resultant vector. Now, this is how we find the resultant of more than two vectors. Let us then go on to apply it to some question so that we can learn as we do it in practical. This question says, 4 forces act as shown below. Calculate the resultant. Now we see the 4 forces. This is 10 newtons, 12 newtons, 9 newtons, and 15 newtons. So in order to find the resultant, we need to resolve the x component and the y component. Now you recall how to do this, right? So let's start with the x component. Now there's something I need to show you here. You see this particular 15 newtons. The angle here is to the, you can see it to the vertical, but you need the angle to the horizontal. If this is 30, this will be 90 minus 30, which will give you 60 degrees. This way, you don't have to bother your head too much when you are solving. This is 60 degrees straight up. So let's solve. Okay, now what we have to do is, let's start from this point here. For our x component, we're going to have, this is positive, so 10 newton cos, the angle here is 30 degrees. Okay, plus, now this is the second quadrant. It means you are going to have a negative value there. So you say minus 12 newton cos, the angle there is 40 degrees. Okay, plus, now this can either count to be the third quadrant or the fourth quadrant, but the angle it makes with the horizontal is 90 degrees. So if I take it as part of the fourth quadrant, I will use plus there. It will now be 9 newtons, but cos 90 degrees. It doesn't matter whether I put it as the third quadrant or fourth quadrant, I will get the same answer because cos 90 is 0. So it's always going to give me a 0, whether I put it here or not. whether it's plus or minus. So you see that it does not affect you as long as you understand the way you have to solve this question by applying the equation direct. You shouldn't have any problem. And then this final one, which is 15 newtons, is in the fourth quadrant, so it takes plus as well. So plus 15 newton cos, the angle there is now 60 degrees. I believe you recall how we got this 60 degrees, which is 90 minus 30. Now, here comes the part where you have to apply your calculator. Now, what would this give you? By the time you solve the whole of this, in the end, you should end up with 6.97 newtons. Positive value. So we have this acting in the positive direction of x, 6.97 newtons. Now, let's find the y component. The y component will then be, we apply the same thing, except that this time it is sine, and we have to take note for where it's positive and where it's negative. Here now, you're going to be having 10 newtons sine 30 degrees. Okay, this is still positive, so plus 12 newtons sine 40 degrees. Now, this we can count whether to be the fourth quadrant or the third quadrant. Is still negative for both of them, and you get negative 9 because it's 90 degrees. Sine 90 is 1. So no matter what I put, it is minus 9 newtons sine 90 degrees. And then plus the final one, which is also going to be negative. So 15 newtons sine, the angle here is 60 degrees. As we did during the first time, so all we need to do here is to apply the calculator. And when you do that, you will get a negative value here. And it is negative 9.28 newtons. That is what you will get for your y component. Okay? Now, all you need to do now is to find the resultant. And the resultant is the square root of the first one here, which is 6.97 in bracket squared plus negative 9.28 in bracket squared. Okay? Now, when you work with this, you have to be careful because this is a negative value here, and minus times minus will always give you plus. Okay? Now, this will give you the square root of 134.699. Okay? Now, once you have this value, you can then find the square root of that using your calculator, and you should get 11.606 newtons. That is the resultant force. So that is all of these force now, these different angles, give you an effective force of 11.606 newton. Once again, when solving questions like this, the major issue is working with these values like this, ensuring that you are able to calculate them right without error. So please, when doing it, take your time, apply your calculator step by step so that you don't make any error. But you can try this yourself and you will always end up with 11.606 newton. And that's the solution to this question. Let us resolve the components of these vectors here. Now we're going to find the x component, the y component, and then in the end find the resultant, which is what the question itself says. So we are told that the figure shows 4 forces acting on the particle P here, and we have to find the resultant. So we see the forces here, 3 newtons, 10 newtons, 3 newtons, and then this 6 newtons. And their angles are given. This is 30 degrees here, this is 60 degrees here. But you see these 3 newtons and this, we'll come to it when we solve now. So here's the solution. The first thing we want to do is to find the x component, okay? Now to find the x component, let's start with this particular force. To the horizontal, this makes what angle? It's already on the horizontal itself. So that makes it 0 degrees. So it will be 3 cos 0 degrees. Okay? Now, this is still in the first quadrant, so plus, all are positive there. So 10 newton cos, the angle here is what? 30 degrees. This we can still count as part of the first quadrant. So plus 3 newtons. Now remember, this will be cos 90 degrees. Okay? And then to this last one here, this is on the third quadrant, so it will take negative. So negative 6 newton cos, the angle there is 60 degrees. Now let's resolve them one after the other. Please, at this point, be very careful as you solve. Cos 0 is 1. Okay? 1 times 3 remains 3 newtons. Plus, what you have here is going to be 10 newtons times cos 30. Now, cos 30, look at it here. Just look up here. You see 10 times cos 30 is sod 3 over 2. So if you solve this, what you are going to end up with there is what? 5 sod 3 in newtons. Okay? Now, when you look at what we have here, okay? Considering what we have here, we have 3 sod 3 cos 90. Cos 90 itself is 0. 0 times this remains 0. You see that now? And then this final part is minus 6 newtons cos 60. Cos 60 is half. That's 0.5. 0.5 times 6 will give you 3. So that's minus 3 newtons. Now look here. Plus 3 newtons minus 3 newtons is gone. So x here is just 5 sod 3 in newtons. Quite simple now, right? Now let's resolve to get our y component. Following the same thing, the angles remain the same, but the signs will change. Now this one is going to be 3 sine 0 degrees. Still in the first quadrant, so plus 10 sine 30 degrees. Still in the first quadrant, so plus 3 sod 3 sine 90 degrees. And then this final one here is in the third quadrant, so minus 6 sine 60 degrees. Now let's solve. Y therefore becomes sine 0 is 0 times 3, 0, plus 10 sine 30. Sine 30 is 0.5. 0.5 times 10 will give you 5 newtons. Okay? Now, plus 3 sod 3 sine 90. Sine 90 is 1. 1 times that gives you 3 sod 3. Minus, now let's do this. What you're going to be having there is this. Minus 6. Okay? Then we have sine 60. Sine 60 is sod 3 over 2. What does that mean? Means we have the minus sign here. 2 in this will give you 3. So 3 sod 3. So you see, plus 3 sod 3 minus 3 plus minus 3 sod 3. That gives you 0 there. So y is just 5 newtons. So the resultant is therefore the square root of the x component, which is 5 sod 3 squared, plus the y component, which is 5 squared. Now, what does this give you? When you solve this part, you get 75, plus this one will give you 25. Altogether, we have sod 100. That is, the resultant is what? Sod 100 is what? 10 newtons. So, the resultant of these 4 forces acting on point P here is 10 newtons. And that's the solution to this question. In this question, we have that 4 forces of magnitude 10 newtons, 5 newtons, 4 newtons, and 6 newtons act on an object in the directions north, west, east, and south. Now, each of these are the respective direction of the forces 10 newtons, 5 newtons, 4 newtons, and 6 newtons. So we have to find the magnitude and direction of the resultant. Now, when you have a question like this, one of the safest ways to solve the question without error is to first draw the vector diagram. That way you will be able to get all the direction and capture it in your calculation, in your solution to the question. So first, we'll draw the vector diagram. Now, it's easy because all we have is north, east, west, and south. So we can just draw a simple Cartesian like this. Okay? Now, what we are told is this. The 10 newtons here is acting to the north. So, to the north here, we'll apply 10 newtons. This 5 newtons is acting to the west. Now, the west is in the direction of the left like this. So, that would be 5 newtons. Okay? Then the 4 Newton acts to the east. So to the east here, we're going to apply 4 newtons. And then finally 6 newtons to the south. So this is 6 newtons. Okay? Now, another thing you need to note is this. Because all the angles has to be to the horizontal. So this 4 newton is acting at 0 degrees to the horizontal. This 10 newtons is 90 degrees to the horizontal. This is 0 degrees to the horizontal. And finally, this is 90 degrees to the horizontal. So all you need to do is find your x component, your y component, and then you can find your resultant, which is the first phase of this question. So let's start by getting the x component. Now, for the x component, what we are going to apply is, now let's start from this part here. This is 4 newtons, is in the first quadrant. And if you recall from what we have been solving so far, the first quadrant all are positive. So you would have 4 multiplied by, now since it's x, it will be cos. So cos, the angle to the horizontal is 0 degrees. Now, the next one here is still in the first quadrant, so it's positive. So plus 10. 10 newtons cos, the angle there is 90. Now, this falls in the second quadrant where cosine becomes negative. So minus 5. Now, the angle there is 0, so cos 0 degrees. And then this falls in the fourth quadrant where cosine is positive. So plus 6 cos 90 degrees to the horizontal. Now, what does this give us? Cos 0, 1. 1 times 4, 4 newtons. Okay? Cos 90, 0. 0 times 10, 0. Now, minus, cos 0 is 1. 1 times 5 is 5 newtons. Plus, cos 90 is 0. 0 times 6, 0. Now, when you work with this, we have 4 newtons minus 5 newtons, and we have negative 1 newton. That's the x component of the 4 forces. Now, let's find the y component. For the y component, these angles remain the same. The only thing that changes here is positive, here is positive, here is positive, while this one will be the only one that is negative. So let's apply it. That is, what we have here is 4, and remember, sine. So angle is 0 degrees. This remains positive, so plus 10 sine. The angle remains the same, 90 degrees. Now, this is also plus, so plus 5 sine. The angle is 0 degrees. And then this one will now be minus. And what we have here is what? 6 sine 90 degrees. Now, y component therefore becomes, now sine 0 is 0. 0 times 4, 0. Sine 90, 1. 1 times 10, that's 10 newtons. Now, this will also give you 0. That is, this tends to 0 just as this tends to 0. Now, this final part here will be minus. Sine 90 is 1. 1 times 6, 6 newtons. So our y component here is 4 newtons, positive 4. Now, all we need to do is find the resultant. So to find the resultant, remember, resultant r equals the square root of x squared plus y squared. So let's apply it. R therefore becomes square root of, the x component is what? Negative 1. So minus 1 squared plus y component is 4. So 4 squared. This would give us 1 plus 16. Now, R therefore becomes 17 in newtons. You can leave it like this. There's no rule that says it has to be in decimal or short form, except when you are solving multiple choice question where you are forced to use whatever you find in the option. So if you have your answer in short form there, good and fine. And if it is in decimal, you can convert to decimal. But for those who like decimal, this is equivalent to 4.12 newtons. So both are correct. Okay, so now we have the magnitude of the resultant. Let's then go on to find the direction. Now, to find the direction is not difficult. You see, this sign we have here is just telling you in what direction the x component is going and the y component is going. So since we have negative x for the component x component, That is, we're going to take it to the left, which shows the negative direction of a graph. Simple. When you have a Cartesian graph, of course, you know this is plus x-axis, this is negative x-axis. This is plus y-axis, negative y-axis. That's just what it means. All this sign here is just showing you direction. Okay? So we have -1 for x-axis. So it's going to the left. Y is positive, so it's going up. So when your y-axis is like this, okay, 4 newtons. The x-axis is like this, 1 Newton. And the resultant is just this line you have here. Okay? So what the question is asking us to find is the direction of this resultant. So it has to go along this path. So we need this angle here. This angle. Let's call it theta. So what do we see here? This is opposite. This is adjacent. And to work with this, with your trigonometric ratio, so, ka, toa. Right? So what do we have there? It means we have to apply the tan ratio. Opposite over adjacent. So tan theta becomes the opposite. 4 over adjacent, which is 1. So this gives you 4. So theta itself then becomes tan inverse of 4. And when you solve this, you find that theta is 75.96, 75.96 degrees. So it's approximately 76 degrees. So once again, it is only when you have multiple choice question that you are forced to use a particular answer. So in a case like this, you can leave your answer like this, or you approximate to the nearest whole number. There's no rule against that. So it's only in multiple choice you have to use what you can find in the options provided. Okay, but this is not the best way to actually show direction of a vector. So you have to show whether it's the northwest, northeast, north south, or whichever one it is. So since this direction here is what? North, and this is going this way. See the direction is going on along this point. Okay, you see that this is north and this is what? East. So we say it is north 75.96 degrees east. That will be the direction of the resultant of these 4 forces acting on the object. Now, I hope you understand this process. Okay, if you have any more question on how you can find or resolve more than 2 vectors, please drop it in the comment section and we'll be happy to explain those questions to you. Now, if you're yet to be subscribed to the channel, we'd like to urge you to please take a moment, click the subscribe button, and you can also hit the notification bell icon. So that way, every time we upload a new content, you will be notified. And please don't forget to like the video and share them so that we can reach many more students like you who need helpful content like this. Thank you so much for following the video so far. We still have more that will come your way, so stay tuned as we keep bringing you more helpful content right here on this channel. Thank you very much. Bye for now.